Thank you for coming. Thank you for waking up so early. All right, so who read the slides? Who read the white paper? Awesome. Who read the Nmap white paper? Okay, today we're going to talk about trying to backdoor big time your hardware. So the idea is to use mostly open source, because we're going to see pretty quickly that if you want to make your own BIOS, essentially, you don't have many options. Either you do it from scratch and you spend the rest of your life doing it, or you take like bits and pieces here and there, and you combine them together to make like something super evil. So not too surprisingly, I took the second option. So I won't release the proof of concept, but it's essentially, I mean, if you take the time to Google a bit, everything is already available. So the big surprise is that the x86 architecture, the Intel architecture, is essentially plagued by legacy. And therefore, what I'm going to present you is not a vulnerability. It's like the architecture is like this, and there is no patch for it. So like some of you may know, for the rest of you, it may be a bit of a big surprise. So there again, there is no patch for it. I think this is a strong motivation to actually share this so that we can enhance the architecture itself. And well, I don't have a fix, so like if you have suggestions, feel free to ping me. I'm interested in seeing how we could do things better. So in terms of agenda, look, I don't usually do backdoors and stuff like that, but if I take the time to do one, I want it to be epic. So I want something like remotely controllable, remotely updatable. I want it to work everywhere, and I want it to be like, you know, bypassing every IDS, IPS, antivirus, and stuff in the world. This stuff is called Rakshasa, which in the Indie mythology is like the devil. Go figure. We'll talk a bit about cryptography. Anybody is familiar with like TPM, trusted computing and stuff like that? Yep. So we're going to see that this doesn't work either. And yep, finally, we're going to see like how to backdoor like a nation state. So think like China, NSA, whatever. Who am I? So like I do security and blah, 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 and that's it. Just one thing, we do a conference in Paris, which is called Akito Agosom. And if you'd like a free trip to Paris, like feel free to submit. Okay, a bit of fun. This is for the media. Who's the journalist out there? Don't be shy. All right, so if you've been hibernating for the past few months, it's very much in the air. There was this mighty report from, so it's interesting in the US. They have like private companies doing reports for the government, for the Senate. And this stuff says, oh, you know what? Computers are built in China and we don't trust the Chinese, essentially. It's mostly FUD, but the perspective is interesting. Like, it's true that actually computers are all manufactured in China and we don't control the supply chain. I mean, when you receive a new computer, who's actually checking for, you know, the integrity of your firmwares? Who does it? No, Chinese don't do it. Nobody does it. Bullshit. Like, I mean, you have a bunch, inside a computer like this, you have actually a bunch of firmwares, right? Like controlling pretty much every peripheral, like your PCI peripheral, like your network card or whatever, and nobody controls that. It's essentially not that hard for a vendor to backdoor it. Can we do better? More FUD. So like, yeah, Chinese is backdooring 80% of the world, blah, blah, Chinese. It's interesting, it's always Chinese, right? Blah, 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 Chinese is the bad guys. In France, they even changed like all the core routers, which were UI routers. So I'm not saying UI is super trustable, but like surprisingly, they choose to favor Alcatel-Lucent, who is also slashing 5,000 jobs worldwide. And is half French, go figure. All right, when it comes to technical stuff, let me introduce you the problem. So this is essentially the Intel architecture. It's built like this. The slower the peripheral, the lower it is. So like, if you have peripherals back from the, the 80s, this architecture dates back from 81. So like, if you have super slow peripheral like floppy disk, keyboards, and stuff like that, it's connected to the super I/O. At the level of the soft bridge, you have like slightly faster peripherals, typically, all your PCI stuff, so like Ethernet card, your hard drives, and stuff like that. At the north bridge level, you have essentially your video card, and if you're rich enough, you have like gigabit Ethernet and stuff like that. And the closer you get to the CPU, the faster the device. One thing interesting, when it comes to TPM, this piece of shit over there, anybody works for Microsoft or Intel? All right, for those of you who've been reading about the next Windows 8, one of the big things is like, yeah, they're gonna use like, trusted computing and stuff like that to ensure integrity of your BIOS and blah, blah, blah. The interesting thing about TPM is that it's a passive ship. So like, if you don't want to use it, you just don't use it. It's software is calling it, but it's not mandatory. If you take an architecture like a game console, for instance, if you're not using the cryptographic chip, the CPU just plain doesn't boot. With TPM, if you have software, who decides not to call the TPM chip, you just don't, and like you just don't use it. So like my motherboard, for instance, has a TPM chip. If you replace like the master board record with another one, who's not calling TPM, well, it's just gonna work, which is awesome design. Let's talk a bit about the state of the art before introducing how I see the problem. So like essentially patching, going low level as being back in the 80s was really a strong motivation. The first viruses like Brain, allegedly built in Pakistan, was already targeting the master board record. Then in the 90s, it became like, when internet appeared, it became more interesting to go for IO level stuff, because doing networking, for instance, from very low level is very tough. If you're doing a real-mode operating system and you're trying to get networking, you don't have multitasking, unless you cheat with like terminate and stay resident stuff, but like essentially you don't have multitasking, meaning that if you want to do a TCP connection, you can send packets, and you're in a blocking state until you receive something. So like doing a full TCP stack in real mode is essentially impossible. So it became more interesting for viruses and worms to actually go higher level and do like, something which spreads across the internet using like email and stuff like that, macros and whatnot. So essentially it became boring. And in 2007, bootkitting and stuff became to the light again with EFI backdoors. The work from the guys from Core Security is actually pretty epic. They published a FRAC article on this too. So they did it the hard way. They were like, all right, we really want to be first to be executed in memory. So we're gonna remove the BIOS and patch another one. Instead of writing it from scratch, they took a legit BIOS, identified the routine which is responsible for checksumming, the integrity of the BIOS, reversed it, patched the BIOS to introduce a new routine, and compensated the checksum. It's essentially doing it the hard way, the stuff I don't want to do. And they managed to do it for Harvard BIOS and Phoenix BIOS. It's pretty remarkable. In 2009, Peter Kleissner, who's a German guy, managed to bootkit, so not only Windows, but also TrueCrypt, in spite of full disk encryption. In 2010, Kumar and Kumar, two Indians, did an amazing job at reversing Windows 7. So they managed to bootkit Windows 7, but they did a lot more than this. They actually released a device driver to be able to mount encrypted drives by BitLocker and stuff like that. And they identified the critical structures in memory for the Windows 7 kernel. And Piotr Bania, who's a guy from, I think he's Polish, or Romania maybe, did a bootkit which is publicly available for 32-bit at least, and he actually helped me with this talk. So like, I'll give him credit when due. And of course, like, or Snare, who gave a talk yesterday morning. Who was at Snare's talk? Was it good? Yeah, pretty epic. So like, he's been working on UEFI. I've been focusing mostly on the BIOS itself, because like, nobody's using UEFI yet. But like, what he does is pretty pioneering and like, will be definitely relevant in a few years. All right, let's talk about Rakshasa. So there again, if we do a backdoor, I want it to be cool. I want it to be persistent, not detectable. When we say stealth, I don't mean like, you know, hiding with a dot, prepending a dot or something like this. I really mean nothing on disk, no forensic evidence at all. I mean, with my company in France, sometimes we do forensic analysis. Essentially, clients, when they detect an intrusion, they start panicking. So like they unplug everything, they shut down the box, and they send you the hard drive. If this happens, I mean, I want zero evidence on the hard drive, so like no forensic evidence. We want remote access, remote updates. I mean, we want something cool, and state-level quality. So if you're a nation state, there are essentially two properties you have to respect. The first is plausible deniability, which is saying, oh no, this was not a backdoor, this was an accident. And non-attribution, which is, no, it wasn't me, it was China. I wanted to bypass, you know, network security, such as firewalls, IDS, IPS. Anybody working for an IPS company, an IDS company, a firewall company? Yeah, you all work on the Deval side, right? Sure thing. I want redundancy in case, like, I mean, if my backdoor gets detected somehow or by accident removed, I want to be able to come back. So we want some degree of redundancy. And of course, I want it non-detectable by antiviruses, but like, this is a joke anyway. So this is a corporate firewall, typical corporate firewall. You can recognize the end user with a fancy computer, the most interesting property being that it's cute. Then you have a bunch of toys in the middle, like IDS, IPS, and stuff like that. And in worst case scenario, you have a proper firewall which entirely segregates internal network and internet. Like, I mean, there is no such thing as, I mean, ideally, you need like proper authentication before accessing the firewall. And you have like proper segregation in the sense like you cannot send like, you know, UDP packets or stuff like that, typically DNS. So let's assume it's a real network with proper segregation of DNS and stuff like that. So what is supposed to happen is this. The user is supposed to authenticate against the firewall, and your toys in the middle are going to analyze the traffic with deep packet inspection and catch like any malicious traffic. What we're really going to do is this. We're gonna put our malware inside the hardware of this box. And like, since we don't care so much about this stuff, I mean, we're gonna bypass it entirely by using the different network stack, using the Wi-Fi integrated hopefully inside the laptop. And we're gonna update the computer from the parking slot or something like this. And so you don't care about authentication and stuff like that anymore. The benefit being, if you don't use the corporate firewall, the corporate network, there is no forensic evidence. So how to do this? Essentially, Rakshasa is built on top of those three software. The first one is called Coreboot. It was previously called Linux BIOS. The idea was like, all right, we like using open source and stuff like that, but there is always at least one firmware which is always proprietary, which is your BIOS, and it's pretty annoying. So the idea was like to have an open source BIOS to work everywhere. They managed to port it on more than 230 motherboards. So, I mean, The official answer from Intel to this talk was like, this is theoretical. Yeah, it's working on 230 motherboards, and that's theoretical. So Coreboot. Coreboot is like the backend of your BIOS. Essentially, it's responsible for detecting all your peripherals and perform a BIOS post. Then you need another component, which is like the upper hand of your BIOS, if you will, which will create in memory your interrupt vector table and make it programmable. So it's like the interface between your hardware and making it programmable. With Coreboot, there is one which is called CBIOS. There is an alternative which actually works with UEFI. So if you want to do something like snare, I mean, you want to merge his bootkit inside my research, you just change CBIOS by, I don't know its name, but like the other front end which is available. I also used IPXE. Who knows what PXE is? Oh, come on, you all suck at networking. So PXE was like, the idea was like to have diskless computers, boot from the network. So you just have a computer with no disk. It has a network card. It's acquiring a MAC address from the network. And the DHCP is also telling you where to download a disk image using TFTP. That was the original design, made to work only from the internal network. IPXE is actually a lot cooler. You don't have to use DHCP, and you don't have to use TFTP either. You can essentially assign you a MAC address over any interface, being it Wi-Fi, gigabit Ethernet, 3G if you want, so any kind of physical devices. And in terms of protocols, you can use like HTTP, FTP, HTTPS, and stuff like that. If you want to look legit inside a corporate network, you're just going to use HTTP or HTTPS. The good thing about Coreboot is that it's so modular, you can take this IPXE stuff, which is supposed to be a firmware sitting on your network card, and you can actually merge it inside the firmware of your BIOS and put all the drivers, which are supposed to be on different peripherals, inside the BIOS itself, and it's going to work. So Coreboot is really like awesome. In addition to this, we need some payloads. The ultimate goal is like to go from the physical layer, the proper hardware, up to user land, or actually kernel land. So we have to go a bit up the stacks, and I'm going to use bootkits. Who knows what's a bootkit? Is it boring? What's a bootkit? Nobody knows? All right, so a bootkit is like a piece of software you're supposed to boot normally on an alternate media, such as a CD-ROM or a floppy disk. And if you boot on this stuff, it's going to patch your kernel in memory and allow you to do something mighty. Either load an unsigned kernel driver in memory, and it's game over, or patch the kernel to remove any kind of authentication. So the one I'm using is the one from Piotr Bania, slightly modified, not to have like super cool graphic designs, because like I don't want that for a backdoor. But the idea will be so it works this way. Your computer, when you start, boots in legacy mode 8088. So it's like 16-bit real mode. So the BIOS is the first piece of software which is executed in memory. It's responsible for finding like your RAM, your hard drive, and stuff like that. From the first bootable hard drive, it checks the first sector, which is a master boot record, loads it in memory at a given address, which is 7C00. It's a linear addressing thing. And jump to the entry point of your master boot record. The master boot record itself is responsible for loading the kernel in memory, right? At this stage, you don't have a libc, you don't have a kernel, you don't have anything in memory. The only stuff you have available for programming is the interrupt vector table, which is programming the hardware directly. So how does a bootkit work? Essentially, it patches interruption 13. Who's been doing MS-DOS programming back in the days? All right, so like for you, it should be understandable. For the rest of you, like. So it works like this. If you hook interruption 13, you hook every access to disk. If you want to read, seek, or whatever, it's very low level. I mean, the kind of access with interruption 13, you have to specify the disk, cylinder, head you want to read from, right? It's that degree of lowness. So if you hook interruption 13, when the master boot record is going to try to load the kernel from the disk, essentially it's going to try to read a sector from disk in memory. And if you detect this, because you hooked the interruption 13, you can like patch what's going to be loaded in memory. And the idea is to find interesting locations inside the Windows kernel, essentially, to like bypass authentication and stuff like that, or inject your own driver. So this is the payload, which is called a bootkit. One cool feature about using free software is that it wasn't me, it's free software. So you have non-attribution. In terms of portability, either you start doing your own BIOS yourself, and maybe you'll manage to support your own box, maybe. Or you use something like Coreboot, and it's a given, you already support 230 motherboards, your option. Another cool thing is like, okay, if you look at the antivirus reports regarding Juku and all that stuff and Stuxnet, so like Juku has been borrowing code from Stuxnet, so like it looks super malicious and it's probably the same group and blah, blah, blah. If you use free software, which is legit, it's going to be super hard for an antivirus to detect it as malicious. Otherwise, it's going to be a false positive, right? Because they are legitimate use for Coreboot, CBIOS, IPXE. It's not evil software per se. So it's going to work like this. We're going to flash the BIOS with Coreboot, and all embedded PCI runs inside the big firmware for the BIOS. Since we want redundancy, we're also going to flash the PCI firmware inside the network card, so that even if the user somehow upgrades his BIOS and stuff like that, we're still on the box. We still own the network card. So unless you flash at the same time your BIOS and your network card, we're there forever. The idea is to eventually boot a payload, so a bootkit, but I don't want to store the bootkit on the BIOS. We're going to boot it from the internet. This allows us to perform remote updates. And in case I want to, okay, the ultimate idea is like to make a botnet from the BIOS. If I ever want to shut down my botnet, I kill the command and control, and the BIOS will not be able to boot the bootkit anymore, and there is zero forensic evidence. So like even if you send your computer to McAfee or whatever, there is nothing, even in the BIOS, which is malicious. It's all coming from the network dynamically. And so the idea will be, in order of priority, we're going to try to boot from Wi-Fi. If it doesn't work, we're going to try from WiMAX, saying we have a WiMAX card, in order to bypass the network perimeter, like I explained before, here. If it doesn't work, we're just going to try to acquire a MAC address on the network using DHCP. If it works, we're going to try to use a static IP address. If it fails, you probably don't have access to the internet anyway. And one cool thing, we can actually disinfect Rakshasa from the internet. So like we can tell it like, you know what, we're going to reflash your BIOS from the internet. Or so either for disinfection or for upgrades. So it works like this. All this stuff, this stack of Coreboot, CBIOS, which is the front end for the BIOS, and IPXE, which is the driver for the network card, are not malicious, and they are contained inside, all of them, inside the BIOS, the custom firmware for the BIOS. And the only thing which is evil, which is a bootkit, is going to be fetched from the internet at boot time over SSL. Any questions so far? That was too easy. All right. So the kind of cool stuff we can use as a payload. We can remove the NX bit. If you do that, everything in the address space becomes executable again. Your heap, your stack, whatever. We can turn every mapping in ring 0, so like in kernel land, writable again. We can remove anti-SMM protection, because okay, I get back to SMM, but essentially the fix for the SMM problem, SMM being the patch mode for the CPU, or the debug mode for the CPU, is supposed to be fixed from the BIOS. But if I own the BIOS, I don't have to patch the fix. So we will see that this leads to a generic local exploit unless you're running in a virtualized environment. We can even disable ASLR from a bootkit. We'll see this. And in terms of bootkitting, essentially, once you can write to the kernel, you can do anything you want in kernel land. Thanks again to Piotr Bania for helping me with the bootkit of Rakshasa. So how do you remove NX? The real question is how does NX work? So NX is a model-specific register, meaning that if you have a CPU which is older than 97 or something, you don't support it at all. So the idea is that you have a flag, and if you set it to 1 in the CR0 register, if you set this bit to 1, memory which is not supposed to be, memory which is supposed to be read-only is not executable. The default being that everything which is mapped is executable. So how do we remove this stuff? It's not too hard. The trick is essentially to use a CPU ID instruction to get the supported MSR model-specific register capabilities of your CPU. If your CPU is older than 97, this shellcode is going to fail, but I assume it's pretty okay. If you have at least this function, 800001, you can get what are all the model-specific register information. Then you check a specific bit in EDX. If this bit is not set, then NX is not supported, so you don't need to patch anything. Probably what's going to happen is that it's going to be set, so what we do is we read and we write back after flipping the bit. The RDMSR and WRMSR are the equivalent of a move to move memory, only using model-specific registers. Too easy? There are other ways to do it. How do you make all the mapping in ring 0 writable again? So if we read the Intel manuals, there again, there is a bit. If you flip it, so bit 16 of control register 0, if you flip it, everything is writable in, everything which is mapped in memory in ring 0 becomes writable again. So you have a 32-bit version, which is essentially reading CR0 inside a standard register, flipping the bit and writing back, and that's it. And 64-bit is strictly equivalent, since by the specification, the 32 first bits of CR0 are always 0. Otherwise, you get a protection fault. CPU update, I love that one. Do you guys know that you can actually upgrade your CPU using software? You can patch it. This is called microcodes, and it's used by Intel and their competitors, but ARM, to upgrade when they actually fuck up. Instead of calling back all the CPUs and changing your CPU, they push a microcode update. What you can do is remove all the updates that the BIOS is supposed to push. Since we're going to do our own BIOS, we don't have to push the microcodes. SMM, is it too hardcore? Too boring? We go to demos? No, it's interesting? All right. SMM. So essentially, Duflo discovered in 2006 and 2007 that the patch mode for the CPU, which is called SMM, System Management Mode, can be abused to execute stuff in a mode which is even better than ring 0. It's like ring -1, because even the kernel doesn't know about it. The idea was that the patch to this problem, this is well beyond the scope of this talk, but like the idea was that the patch has to be pushed in the BIOS. If you read, this is from the Intel manuals, they say the BIOS can use the blah 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 flag to initialize SMM space and lock down the SMM space. But of course, if I control my own BIOS, if I do my own BIOS, I don't have to patch this stuff. Interestingly, Coreboot doesn't support locking the SMM zone anyway, so my super elite shellcode to allow SMM is a NOP. That was hard. Okay, disabling ASLR. This is slightly more hardcore. So ASLR in New Zealand is set by the equivalent of execve, or create process if you're a Windows lover. So it has to be done in kernel land. If we can patch the kernel, we can patch the stuff which is supposed to seed the ASLR. So in the Unix world, it happens by opening /dev random, picking a seed, and adding this seed to the base address of your the mapping of your binary. Am I speaking Chinese? All right. If you're in the Windows world, the guys, I mentioned you the Kumar and Kumar guys from India, they discovered where the seed is on the Windows kernel. So like if you patch it with something repeatable, like 41414141, well, the mapping is repeatable forever. So like even if you don't use a bootkit, if you put all this stuff, your memory is writable in ring 0, you don't have ASLR, you don't have NX, so like you're going to be just bang vulnerable to the next vulnerability, even if like the rest of the world is not supposed to be affected. So if we implement all of this, we're going to level this, lower down the level of security of any operating system. It's not specific. I mean, removing NX, for instance, is not specific to whatever operating system you're using. And you effectively back in 97 in terms of security. There again, there is nothing on the hard drive. So in terms of forensic, nothing to check. Now, I also want a remote payload. So like we're going to try to boot a different version of the one created by Piotr Bania, which is honestly the best so far. Yep. Sorry? I can't hear you, mate.
Could you check the server that IPXC is pointing to?
The server that IPXC is pointing to. What do you mean by check?
Well, you're saying there's nothing to find on
Yeah, but it's a server somewhere on the internet that I control, right? So like it's not like you could just, you know, I mean, unless you own the entire internet and you can check it by yourself. In terms of forensic stuff, there is nothing on the hard drive. I mean, even on the BIOS, not only there is nothing on the hard drive itself, not even like file carving and shit like this. There is actually nothing malicious on the PCI drivers either. So like, if you take just the box by itself, there is nothing malicious. Now, if you're telling me, oh, but you're downloading something malicious, yeah, it's what I'm saying. So yes, I agree. There is something malicious at the end of the day, but it's popped from the internet, and the attacker can shut it down at any time. If he suspects that, you know, the FBI is knocking at the door, it just shuts down the command and control, and that's it. Yep. Any questions? Boring? Too easy? Okay, we're going to go for the demos. Just a bit of summing up. So there again, we do not touch the disk. There is nothing to find for an antivirus. The code which is on the motherboard is not hostile. So like, antivirus said, oh yeah, but we're going to perform an upgrade, so like we'll be able to detect like firmwares and shit. Like, no, man, like there is nothing hostile. We're going to see with the demo how to remotely boot an alternate payload. Of course, if you're using full disk encryption with TPM, there is a slight problem, because if you're using trusted boot measurement, and you're actually using TPM to store your encryption keys, it's not super. I mean, even if we boot an alternate media, we will not be able to decrypt your disk. but it's not too bad. I can present you a fake TrueCrypt prompt or a fake BitLocker prompt. Yep, just a sec. I can show you a fake BitLocker prompt, which is going to send me back your password. So like next time I knock at your door, I take a copy of your hard drive, and if I know your password, I don't need anything else. Yep, tell me, Tim.
If you really change the content of your BIOS in that sense that you have set the TPM bits, I think it's 7 or something like that, such that it will do a signature over the BIOS that is loaded, then it will not give you the prompt. It will tell you your box is fucked, and it's not gonna basically give you any option to input the key that you're looking for. So
yeah, okay, so I see your point. The thing to understand about TPM is that it's passive. So like if I get to flash the BIOS, even on the latest boards where the BIOS is signed and you cannot push like upgrades, if I don't have the permission of the BIOS because I flash it physically using a FPGA, and I don't call the TPM ship because it's only software-based and not a hardware-enforced security, I don't have to use it. And no, it will not be fucked because the firmware which is on the BIOS is written by me. So like there is no such thing as a, oh, but like I'm gonna use security, I'll shoot myself in the foot. Yep. But good question. You guys got his point? Okay, it's getting boring, seriously. Let's go for the, just one thing which is cool, I think. Coreboot has the capability of emulating the CMOS, which is essentially an NVRAM memory. So we can use the NVRAM as storage. If I want to use like, I can use it to store my own private keys, for instance, or stuff like that, which I find pretty cool and old school. You know what? Let's go for the demos, and I get back to this. Okay, so I'm going to start a Wireshark. Okay, since I obviously did not backdoor my own box, I'm going to use QEMU, or more precisely KVM, which is the same thing with kernel enhancement. So the command line is like this. We're going to specify, instead of using the default BIOS from KVM, we're going to specify the Rakshasa bin, which is really something you could flash on a real hardware on 230 motherboards. We're going to ask him to have like a network connection. So it's bound to essentially my user LAN connection. And we're going to boot this hard drive, which is essentially a Windows 7 64-bit. So we can even go full screen, maybe. I need a volunteer to type my Windows password. Frank, you know my Windows password?
Stuck to the bottom of your keyboard.
Well, like, can you come and type anything? You don't have to put your real password, mate. Thank you. Quali sold me. Okay, since nobody works for Microsoft, you guys don't care if I did not register this copy. Okay, so this one is actually Windows 7 Service Pack 1 on 64-bit. In terms of bootkitting, well, so Windows 8 will be a different kind of challenge, but like so far, for what's used in production, this is as hardcore as it gets. You can upload here, and then I explain you how it works. No, you don't? All right. let's look a bit at what happened in Wireshark. Okay, so Ubuntu is downloading a bunch of stuff. Okay, this is the first TCP connection. So interestingly, the BIOS itself is doing a HTTP connection to download a JPEG, but sending a few interesting parameters, like it's specifying its IP address, its MAC address, the network mask, the gateway. So like this could be done over the internet, right? Currently, I'm cheating. It's downloading from my Apache running on the host, but this definitely works over the internet too. As an answer, we're sending back IPXE configuration. We could hard code the parameters and stuff, but if I want to have a proper botnet with a command and control, it's much better in terms of flexibility to tell him, hey, you know what, from there, you can boot anything else. In this case, yeah, so I commented everything, which is very smart. I'm booting from that one. So essentially, it tells him, you know what? You're going to find a kernel at this address, and you're going to find an initRD at this address. So you download them over HTTP. We could put HTTPS, but for a demo, it would kind of suck because you wouldn't see anything. And then you boot. So then what happens? Well, we can see that the second HTTP connection is actually downloading memdisk, and that the third HTTP connection, hopefully, is actually downloaded the initRD, which is nothing less than my bootkit. Okay? So if you do this over HTTPS and specifically over Wi-Fi, well, like in terms of forensic evidence of the network, there is back to the slides. So IPXE has a bunch of configuration files. You can essentially tell him, first off, we want an IP address. So we could use Wi-Fi, we could use WiMAX or whatever. It's capable, it has drivers to understand all those stacks. So what we try is like, you try to get DHCP. If it doesn't work, you set all those static parameters. Then we can do stuff like, since we can do a remote HTTP connection, we can send to the command and controller, which is just a random blog. I use the one from Akito Agosom in this example. You're going to send like your IP address, your MAC address, your network mask, your DNS, your gateway, and your domain. Why not? Then you're going to download a kernel. Before downloading a kernel, you're going to send me an email from the BIOS so I can keep track of you. I'm going to show you one such email in a second. So like in this case, I actually used a vulnerable host on the internet, abusing a web service, sending a mail like from Rakshasa whatever to andrezin@gmail.com with the subject like, you got home, bitch. We can do router farming. Like if I'm actually attacking home users, I can definitely change like the firewall settings. Like, okay, I'm authenticating using admin password against your home router. And what I'm doing is like on the firewall, I'm disabling the firewall, or more precisely, enabling open all the ports. You can do it a few times if you want. And then we're gonna chain over an HTTPS configuration, meaning that instead of hard coding my configuration inside your BIOS, which would be forensic evidence, we're gonna fetch the proper configuration dynamically, which can change over the internet, which is what we just saw as a demo. Then, as an example of configuration, we can say, okay, forget all what we've done so far. You're gonna download me a kernel over FTP, why not? initRD over HTTP and boot the stuff. So what we just did as a demo is exactly this. We connected to a remote command and control over HTTP. The command and control contained another IPXC configuration, which told the BIOS where to find a mem disk and an init.rd, right? And the init.rd being the bootkit itself. That was a super cool demo of that. I have a video with the same if you want. So if we look on the Apache side of things, I can actually show you my own Apache, since we just did the demo. So if we look at access.log, the last queries contain like the IP address of the victim, the net mask, the gateway, and stuff like that, which in terms of tracking is pretty cool. We can have it send an email from the BIOS. You can actually send emails to yourself abusing a web service or whatever. This is one I did for my previous demo. So like it's sending me your IP address, your MAC address, your net mask, and whatnot. From there, how can we properly build a botnet that nobody can shut down? Just to specify, of course, I work on the good side of things, and I only do this like for research perspective. So we could use HTTPS, and we can actually use client-side certificates. I saw people telling me like, oh yeah, but like if you go through my firewall using HTTPS, I'm gonna sniff your traffic because like we do MITM of everybody. Yeah, but like if I use client-side certificates, the HTTPS connection is gonna fail, and period. You're not gonna sniff anything. I mean, bottom line is, if vendors can do secure updates, so can do malicious software. It's you cannot have it both ways. So if Microsoft is capable of using client-side certificates and signed updates, I can do that too. And this is all built in IPXC. That's cool or what? I didn't have to code anything. So the big problem with botnet these days is that your command and control, even if you're using like fast flux and stuff like that, is subject to hijacking. If law enforcement hijacks the command and control, essentially they're pretty reluctant to do it, because if you have like people, with medical equipment and stuff like that, which are infected, if they actually shut down the botnet, they may kill everybody too. But like, they sometimes do it. They did it for the DNS hijacker recently, for instance. So like the big problem, the big one point of failure of your botnet is your command and control. What you can do with your command and control is actually rotate your command and control. Since we have client-side certificates and shit, we can rotate over all the internet. So what you're gonna do? You're gonna shut down the whole internet to shut down my botnet? Of course not. It means that my command and control, if I have a few hosts on the internet and I use every possible IP on the internet rotatively as a command and control from my BIOS, I'm not gonna control my botnet every day, but it doesn't matter. Like if I can update, say, once a month and you cannot shut it down, it's good enough. So how do you shut that down? You can't. Cryptography. Anybody works for cryptography and no? Okay, so like we said, TPM is actually a problem. If you do a botnet, if you do a malware which is doing what we just did with against a hard disk which is encrypted using strong cryptography and TPM, you won't have access to the data. But it doesn't matter. What you can do is actually put a fake prompt for TPM, BitLocker, for BitLocker, TrueCrypt, or whatever, then disinfect yourself. I show you how we disinfect Rakshasa. And then the measurement Tim was talking about is going to be all right, because on next reboot, you restored everything. So like your core measurement of trust is actually correct. It's the original BIOS, everything, I mean, the TPM register checking for integrity in memory is going to be all right, and you'll be able to decrypt your disk again. Only the bad guy will know your password. You can do even cool stuff like trying to brute force TPM from the BIOS. I showed that at DEF CON like a few years ago. And yeah, there again, we can disinfect anything. Worst case scenario anyway, what's going to happen is that, okay, the user is going to say, oh, BitLocker is not happy, I cannot decrypt my hard drive, something failed. And then what? Like, you want your data back, right? So like, you're going to decrypt you're going to unseal your TPM, say, enter your passphrase, tell him to re-encrypt the drive, and you're going to re-encrypt and seal your hardware. You don't agree with that? With the TPM thing. Mate, like, it happens every day with SSL. It's like, you have SSL prompts telling you, like, but not for you. Yeah. And you lose all your data. Damn, I need to find something else.
Seriously, what's better? It's like my pawn or your pawn?
Okay, Tim, I see your point. I see your point, but the big thing is when you buy your box, it's not encrypted. Your hard drive is not encrypted. So like if the supply chain is actually installing Rakshasa, if the Chinese do or whoever delivering you your laptop, you're actually going to seal your hard drive with Rakshasa on. Yep. And like, if you try to remove Rakshasa, you lose your pawn and your hard drive and shit. But my bootkit will actually be on your motherboard forever. And this was the point of, I mean, the whole point of this talk, right? Oh. So I see that you have bad influence from Jerome, who works for an antivirus vendor. So we're going to discuss a bit of antiviruses. If you ask me, relying on antiviruses against 0 days is like putting lipstick on your box. I'm going to prove it to you. So like the bootkit, the main bootkit, which I used as the core of Rakshasa is the one from Piotr Bania. It's called Coreboot. If you send Coreboot, which is 5 years old, to VirusTotal, 2 antiviruses detect it as malicious. And not your employer buddy. No. If you pack it with a super hardcore hidden packer, LZMA, which is like the default packer for everything, including nowadays the Linux kernel, but also like virtually every PCI device, the detection rate falls to 0, okay? So in terms of detection, dude. 5 minutes, all right. Realistic attack scenarios. So like, what happens if like you own a box remotely, like a server or whatever, and you want to push Rakshasa? It's like, my main attack scenario was like, okay, I own the hardware already. If you get a remote shell, can you actually install a backdoor at physical layer? Turns out you can. If you're using Linux, there is just a tool which is generic to flash any BIOS. If you want to do it on Windows, well, it's a, lower, it's you will have to pivot of the master boot record because essentially you will need to use the Linux tool. But it doesn't matter. Like you flash the master boot record, you boot a small Linux which is like 1 megabyte big with just one tool, which is a flashing tool plus the BIOS firmware image, and you flash the stuff from Windows 2. What could happen is also you could buy from eBay a network card which is already infected by Rakshasa. And in this case, if you change a peripheral on your box, you actually have to unseal your TPM, right? So in terms of detection, like, sorry, mate. You can even like backdoor an entire data center by telling VMware, okay, I want to use a new BIOS image. Instead of using the legit one, I'm going to use Rakshasa instead. And then you backdoor all the guests in the entire data center. Remediation. So like, there again, it's a physical problem. I don't see Intel enforcing the use of TPM from hardware. So there is essentially no fix. What you can do is detect. So what you could do is every time you buy a computer, take a measurement of all your firmwares, including like the BIOS, but also like every firmware on every peripheral, including like your network card, your video card, and stuff like that. You cannot do that by booting your computer, because if you do it, you implicitly trusting your computer already. So you need to use it to do this using a physical FPGA device, which is going to extract the firmware from every physical device. This is costly. And I mean, and who has the expertise to do this? Call me. I'm expensive. And then, like, if you suspect there is an intrusion, you do the same thing. You, using an FPGA, you extract the firmware and you compare the MD5 checksum plus the SHA-1 checksum, because you don't know if the Chinese actually, or NSA actually got MD5 collision or whatever. It actually happened with, which one was it, Juku? Which had an MD5 collision for Microsoft updates. Yep, so we get like MD5 plus another one. And realistically, I mean, given the cost of this compared to the cost of your hardware, the best solution I can offer you if you get an intrusion is to throw your hardware away. Fuck it. Yep. So that's the kind of self-powered slot you need to extract the firmware from a BIOS or socketize your BIOS. Okay, I sort of bullshitted you. I told you I can remotely flash your BIOS, which is true. What if I want to flash also the network card remotely? The problem being that if you want to flash the BIOS, there is a generic tool to flash every BIOS in the world. But if you want to flash remotely a network card, for instance, it's very vendor specific. So how do we go around this? Well, like we saw previously, IPXE actually allows you over HTTP connection to send back to the command and control your MAC address. If I know your MAC address, I know your WIN number. If I know your WIN number, I know the network, I know the manufacturer of your network card, and I know which tool to use to flash your network card again with a specific firmware. So it all works. And this is not a hack. It's actually documented on the IPXE page, and it's a feature which is supported, which means I don't have to maintain the software, which is even better. How do you backdoor? Like, so we mentioned non-attribution and plausible deniability. Non-attribution is a given. You didn't write the software. It's fucking open source software anyway. So you can add some strings in Mandarin. They love this usually. Like, you change your locals. You know, we're monitoring the internet. There are like 20 groups, and they're all Chinese, and they're all evil. And because like they're changing their locals to Mandarin. Fuck that shit. In terms of plausible deniability, I suggest instead of, if you're a manufacturer from China and you want to own the world, instead of actually pushing Rakshasa on it, I suggest using a benign vulnerability. So a good example of a super cool benign vulnerability, the one from Duflo, the same guy as the SMM stuff, he found a remote, listen to this, a remote vulnerability on network firmwares on your network card for Broadcom cards. It's like, let's say, 30% of the market. It means you have this network card, whatever operating system you're running on it, he sends you one packet and he gets a root shell. So from there, So it's not default. There is a configuration, the configuration stuff, there is a configuration flag. You need to have a remote administrative blah, 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 which is not set by default. I suggest you actually ship a board like this, and you just like put the default configuration, which is handy, on. And if you do that, and and the end user actually discovered this stuff, you say, it was a mistake, and that's it. That's the plausible deniability thing. It's much better than saying, yeah, I backdoor your stuff. More demos. I take 5 minutes, guys. Sorry.
Hurry up.
I will.
Every time, Andrew.
I know.
Every time, mate.
Don't invite me. I think you're gonna like that one, actually. So people tell me, oh yeah, but like your BIOS doesn't have like cool graphics and stuff. From a BIOS, you can actually have stuff like that. I so wanted to do this at Ruxcon. A last one. Okay, if you're backdooring someone who has like, okay, let's say I'm backdooring someone on the same network and we have a SAN. You can actually boot an entire operating system from the network. This is a Windows which is self-contained inside a CD. Looks legit. I mean, the size of the CD, it's realistic. Like, I got this idea from this book, which was sort of bullshit. You guys read this Millennium stuff? I stopped reading where the chick like was booting from a remote hard drive over the internet and stuff like that. And I actually thought, like, you know what? From a SAN is doable. If we look at the size of the Windows CD I'm using right now, it's like 97 megabytes. So if you have gigabytes internet, it's going to take like seconds to actually download it. Cool or what? All right, so the other payload you can use instead of CBIOS, if you want to use UEFI instead of a proper BIOS, and if you want to use the mighty backdoor of Snare instead of mine, you can do exactly the same thing. You can do exactly the same thing. You just use Tiano Core instead of CBIOS. This is not a vulnerability. There is no patch for it. You're fucked. Any questions? Thank you.